Here's the short story. About 2 years ago, I saw a video from Ben over at Applied Science about laser diode self-mixing interferometry. Totally cool concept. Had no idea these little laser pointers and such actually had the ability to do this, and I decided to do it myself. As usual, I got busy, I got distracted, I got pulled away to other things, I got interested in other projects and other random fluff, and ran into a lot of my own ignorance about certain things like using op amps. Before finally, over Christmas holidays, I had basically a couple of weeks solid where I mostly devoted myself to digging in and learning about this and really trying to get something off the ground that was neat and useful, rather than start from the beginning and never actually get to the end. I figured this first video would just be an overview of what the current state of things are. So I have purchased a number of tiny little laser diode, 3-terminal laser diode modules and the housings that go with them. Put them together with 3-terminal, 3-pin, nice dust-proof, waterproof connectors, and then just permanently sealed them in. The original laser diodes I put together with just loose wires and female connectors inside, which were horrible for the electrical connection, but they did work. I just decided to replace this very stiff 22 gauge solid core wire with a much nicer connector. The laser diode is focused about 10 centimeters. It's in a little bench vise which holds it nice and steady. It's feeding into this interface circuit, which at its core is still just powering the laser diode with a constant current, even though I'm controlling voltage through resistance, so it's not really constant current, it's not really proper, but at the moment it's working at the low powers that I'm putting through these diodes. So I'm powering the laser diode, and I'm able to change the amount of current that's passing through the laser diode by this 200 ohm 10-turn precision pot, which is in series with a 100 ohm minimum resistance, just to make sure that I don't fry any laser diodes, which of course I have many times. And then it's being fed into an MCP 5021, I think the number is, but it's an op amp that has a built-in 2.5 volt or half rail-to-rail reference, which is really nice. And it's amplifying anywhere from 100,000 to 1,000,000 times whatever current is coming from the photodiode. This little potentiometer here takes the 0 to 5 volts that comes off of the op amp, and I can scale it so that instead of 0 to 5 volts, I get 0 to 3.3 volts if I want to send that to one of the newer microcontroller analog inputs, or even less. Right now it's about half, so I'm getting a peak of 2.5 volts, which is pretty safe to feed into any of my audio interfaces and all of my microcontrollers and all of my analog to digital converters. The last thing that I added to this, unfortunately, was a USB-C interface that supplied power either direct to the circuit when the battery wasn't being charged or through this battery charger. And unfortunately, adding that added a whole bunch of electrical noise from whatever it is that this battery charger is doing, regardless of whether there's a battery in the charger or not. So I can't really supply it from the USB-C directly right now. I'll show that to you later. But with a large value capacitor across the positive and negative rails, it helps with the noise. Right now, this is only really useful direct battery powered, so I can still charge the battery. I just can't use the circuit while charging the battery. So firing this up is pretty straightforward. I start off with the potentiometer at its lowest level, battery in. And initially, there's nothing. If there was something, you'd be seeing a red dot coming off the laser. It's a very cheap Amazon laser diode. It doesn't really even have a manufacturer associated with it, much less a data sheet. But it runs about 2.2, 2.4 volts and seems to work well as the interferometer. Actually, it did turn on eventually. Very, very, very dimly, I can see the dot at the bottom of the piezo disc. But it's very, very low current. Right now, it's pretty much acting as a glorified LED. It's not really acting as a laser. It's not lasing. But as I increase the current, it will, at one point, suddenly get brighter. And then I stop and I wait to see if I need to continue to adjust it. The output, although I've got a couple of options here, the output after this potentiometer that scales the 0 to 5 volts from the op amp down to 0 to 2.5 volts is just going out to a TRS breakout. And I'm using the ground and the ground pin, the blue, and the right channel, the green. I'm passing it into a 6-way headphone splitter so that I can do things like attaching an actual speaker, an amplified speaker, to hear the output, and plug in another TRS breakout that is feeding my oscilloscope. The piezo disc here is actually like a vibration pickup that you could attach to a musical instrument and then feed to a microphone input so that you could kind of sort of have an electric version of whatever acoustic instrument you're using. Piezo elements can not only produce a voltage when you flex them, but by applying a voltage, they will flex, they'll deform. I have this piezo element connected to a function generator, and if I turn on the function generator, right now it's about 8 hertz and just a sine wave. You can't hear anything, you can't see anything, you can't see anything because piezoelectric crystals barely move. We're not talking about a big speaker like this that's electromagnetic, where the speaker will move back and forth up to several millimeters on a loud sound. Piezo elements only flex a few micrometers. So if I drive this to something that's more of an audio frequency, (866 hertz), you can certainly hear that, but you're not going to see the element flexing. I don't even want it to be audible right now. I want it to be very slow. So I'll bring it down to about, let's say, 10 hertz. So here's, on the scope, you can see the yellow is the 10 hertz sine wave, 20 volt peak to peak, that's going to the piezo and causing the piezo element to flex just a tiny little bit. If I aim the laser at that element and I increase the current to the laser, somewhere around 23, 24 milliamps through the laser diode, you'll see the laser dot suddenly get brighter. I just realized that my little battery circuit is not actually doing what I intended it to. So I need to turn it on first. Little click. And that'll be a lot easier to focus. So I have a nice sharp dot right there. And now with the 10 hertz sine wave causing the piezo element to flex 10 times per second, and the laser dot reasonably focused on the piezo disc itself. If I increase the current through the diode until it starts lasing, probably about there, and then adjust the focus. So I'm going to increase the current a little bit. Now that's probably the sweet spot for this. So, what the heck are we looking at here? So let me reduce the frequency of the function generator first. So in interferometry, there are two waves that can interfere destructively or interfere constructively. Constructive interference makes things higher amplitude. Destructive interference reduces the total amplitude. In your standard interferometer, you would have a laser source that hit a beam splitter. At the beam splitter, that one beam of laser light, one beam would continue towards a target or a mirror, and the other portion would go to another mirror, then bounce off those mirrors and targets back to the beam splitter, through the beam splitter, and they would be able to both reach a detector and constructively or destructively interfere depending on the two path lengths. In the case of a laser diode, what you have is the laser diode is making laser light, but some of that laser light is going back to a little monitor photodiode and hitting the diode directly. The rest of the laser light is going out the front of the laser diode through the laser, being focused down onto this dot, coming back to the lens, and some of that light is bypassing or missing, or whatever you want to call it, the laser diode module, and also hitting the photodiode. So you end up with some laser light going two different directions, and this laser light being bounced back to the photodiode, where that light can constructively and destructively interfere on the photodiode, which is a light sensor, and create a change in the current that's being created by the photodiode. And that tiny change in current is what you are hearing as a cycle. So the neat thing is, this is a red laser diode. It's about 650 nanometers. The length of one wavelength of the laser light is 650 nanometers. If the difference in path lengths between the laser going back to the photodiode and the laser going out and back to the photodiode changes by 325 nanometers, you get one cycle of constructive interference making the laser dot brighter, and one cycle of destructive interference making the laser light a little dimmer. So you get, for 325 nanometers distance change here, you get one sine wave of light and dark. That sine wave of light and dark is becoming an electrical signal that is a cycle of light and dark, a cycle of more and less current, that is then amplified a lot, 100,000 million times, and being fed to my speaker, to my oscilloscope, as a voltage signal. So you're hearing the voltage coming from the speaker, and you're seeing the voltage as the blue trace on the oscilloscope. If I increase the frequency, now, here's a couple of really awesome things. One, since every 325 nanometers in the change of the length of the laser, well, in the change of the distance, really, between the laser diode and the piezo disc, moving back and forth just a tiny bit, every 325 nanometers results in one cycle. So if we look on the oscilloscope, what you can see is that when the voltage out to the piezo is a positive peak of 20 volts, which means that the piezo has moved as far in one direction as it can, you get fewer, and in fact a stopped change in the voltage. Then as the voltage heads towards zero, the rate of change of voltage and the deflection of the piezo disc is at its maximum velocity. And you get many cycles per second. Then it reaches the negative peak, slows down, stops to reverse direction, and accelerates in the opposite direction to a maximum micrometers per second velocity. And this repeats over and over. It's a very easy pattern to see. At the zero crossing, it's moving at its fastest. At the positive and negative peak, at the end of travel of the piezo disc, it actually stops moving. If I stop the oscilloscope for a second, turn on the cursors for a moment, if I go to approximately the positive peak and approximately the negative peak, and then I count the number of cycles between the negative and the positive peak, disc deflected all the way one way, disc deflected all the way the other way, and I count the number of peaks. 1, 2, 3, 4, 5, 31. Call it 32. Maybe 33, but let's call it 32. What this means is that from one end of travel, where the disc is deflected as far as it's going to go toward the laser, and to the other end of travel, where the disc has moved as far away from the laser as possible, the displacement is 32 cycles times 325 nanometers. 325 nanometers times 32 is 10,400 nanometers, or 10.4 micrometers. So right now, at the amplitude that I'm sending out, the plus and minus 10 volts, this disc is flexing back and forth 10.4 micrometers, and I can measure that. It's flexing 10.4 micrometers one way, and then it's 10.4 micrometers back the other way. If I can count those cycles in both directions, I would be able to measure position. But even if I can't follow the phase, which I do want to, I can still pretty much convert the frequency into a velocity directly. Something that I found really interesting about this version of my circuit, though, is that there is an apparent difference between the wave shape when the disc is flexing one way versus the other way. If I zoom out just by one and put 2 cycles on the screen, and I'm going to get rid of the cursors for a second because they're just annoying. If I stop this and I zoom in on this half cycle where I'm going from the negative voltage peak to the positive voltage peak, you can see that the wave shape is slightly skewed to the right. These triangles, they should be sine waves, but I guess the op-amp is saturating a little bit. But it's not quite symmetrical. It's actually leaned over to the right just a little bit. But then I zoom back out, and I go to the other half cycle, where it's going from the positive to the negative, and the piezo disc is moving the opposite direction. The wave shape is now leaned over to the left. I don't know whether that is related to it being slightly on one side or the other side of perfect focus. I would love to know, but the fact is that if I can capture these waveforms perfectly and characterize them based on their skewness, I can not only get a number of cycles, which gives me a displacement, but I can also analyze the shape of the waveform and the phase and be able to get a very solid position measurement. If I keep the same frequency and instead reduce the amplitude, I'm not going to go too far for a reason that I'll tell you in a second, but it's really obvious that now that I've reduced the amplitude to about plus and minus 5 volts instead of plus and minus 10 volts, if I count the number of cycles now, roughly, very roughly, now instead of 32, I get roughly 1, 2, 3, 4, 18, 19. So from 32 cycles times 325 nanometers at plus and minus 10 volts to 18 or 19 times 325 nanometers at plus and minus 5. And it's not a very accurate measurement because I don't actually know if I've halved the voltage exactly. I probably haven't because the displacement isn't going from 32 to 16, it's going from 32 to about 18, so I'm probably a little more than half the original voltage, a little more than half the original displacement per cycle of this piezo disc. So what happens, you might ask, if I just turn off the function generator? Now I have a seismometer. And I'm going to let this run for just a minute or two, because if a large truck or an airplane flies over, you will absolutely hear the change in the audio.